Thank you very much. So for those of you who missed the State of Julia talk, my name is Keno Fischer. I'm one of the core Julia developers. Been working on Julia for more than a decade at this point. And this talk is about binding partitions, aka constant redefinition, aka structs work now, aka constants are no longer constant. What's up with that? If you want to follow along, I'm going to go through some of these slides pretty quickly. There's a QR code up there, and you can find the PDF version in the releases section of the GitHub repository. OK. Oops. There we go. How many people here know what revise is? OK, all but 2 people. Great. So revise is the way that we have in Julia that lets you interactively apply changes that you make to included files or packages to the current session of your Julia process. So an example way that you might do that is this one. You have a file called struct.jl on the right. And declares a struct called point with 2 fields x and y. You create a new point called p/rig, and then you go and you edit it and add a new field called z. And now what happens? Well, in Julia 1.11, the answer is badness. You'll get an error, invalid redefinition. You probably can't construct it anymore because revise tried to add the new constructor for 3 fields to it. So even if you said you don't care about the error, you'll just keep using the old field. Your Julia session state probably was corrupted. And in general, this is one of the primary reasons that people have often had to restart Julia nowadays, because revise is pretty good at handling everything else. So how many people have run, of those who have used revise, have run into this exact problem? OK, basically everybody. So I fixed this. Thank you very much. So this is fixed. So if you're using Julia 1.12, this now works. So if you add the new field, it basically works as you expect. It'll create a new type called point, and you can even still access the point that was created before you edited the struct, although it has this weird @world macro in there, and that's what we'll talk about. I just put a little gag in there. OK, let's talk about bindings. So this talk is mostly about the internal representation of bindings and how Julia understands what any particular name that you refer to in your program actually refers to. There's a little bit more user-facing documentation on world ages and binding replacement that's in the docs, so I'm not going to duplicate too much of that. So this talk is mostly about internals. But to understand what's different in Julia 1.12, I think we need to start with what used to be the design in Julia 1.11. So let's say we have some symbol in our program, and we want to know what it refers to. The first thing that happens is that lowering decides whether it's a local symbol or a global symbol. I'm not going to talk about lowering here. There were various talks at other JuliaCons and this JuliaCon on lowering. But let's suppose that lowering decided that some symbol is a global. How does it know what that symbol actually refers to? Well, the answer is that inside the module struct, there is 2 tables, one for all of the other modules that you've called using on, and one that is a table that maps symbols to something called a binding. So on the slide here, you can see the definition of struct binding. It has a value in there. It has a global ref in there. It has an owner field, which is another binding, or rather, pointer to a binding. If you're not familiar with Julia, it has a type field, and it has some flags. Now, global ref is basically the same as a binding. except that you can have multiple of them, and you can have them even if they don't exist in the binding table. It's a little bit of a historical split. So in Julia 1.11, basically the only difference between a global ref and a binding was that you could never have a binding if it wasn't in some binding table. On Julia 1.12, this distinction is basically completely erased, and you can basically treat them interchangeably, and in fact, we may merge them internally in the future. So I put global ref on the slide, but I won't talk about global ref for the rest of this talk. But I know this can be a little bit abstract, so let's work some examples. So perhaps the simplest possible example, both of these tables are empty. You're not using any modules. You haven't declared any bindings. What happens if you look up a global variable? Well, you just get an undef error. Simple as that. I should point out that this situation basically never happens because you usually always have using base or using core in your module. So I don't even think we actually implemented the optimization for this case. But to simplify, in theory, everything is empty. You just get an undef error. So let's look at the simplest non-trivial case. I say const x equals 1. My binding table gets a new entry for x. I get a new binding object that has value 1, type any, and the flag set to const. And again, this is the 1.11 design, and I've sort of shrunk down the representation a little bit because we'll have a little bit more of these on later slides. But the notation is the top entry in the green node, which is the binding, is the value, the middle node is the type, and then the bottom row is the flags, and the little arrow that comes out of the black circle on the top right is represents the owner field. So if you declare const, you have a single binding, value of 1, const flag set, owner field points to itself, and the type is any. Globals look very similar. It's basically the exact same, except the const flag is not set. Type globals, basically the same, except the type field is int rather than any. You get it. This is simple stuff. And please give a thought to me making all of these diagrams that I show for like 20 seconds apiece. Okay. Now, a little more interesting case, how does import get represented on Julia 1.11? So we're declaring a module A, we're putting a const x into it, then we're importing it, and what this does is it creates a new binding object in main whose value and type fields are completely unused, but the imported flag is set on it, and then the owner field points to actually there's some other binding over there, and then most operations on the binding in main, like is it const, what's the value of it, those kinds of things will actually get redirected to that other field over there. There are some differences. For example, you can't assign through imported bindings, so if you say x equals 1, that'll be an error. But for all intents and purposes, it's basically just a redirector. So it basically says, okay, look at this other binding over there. And this is, I say 1.11, but this has basically been the design since the start of Julia. So this applies up through 1.11. Even more complicated example, 2 imports where I have a module A and then I have a module B that imports it, and then I import the binding from module B. The thing I want to point out on this slide is that the import point, so the owner field points to the ultimate binding that gets imported. So the binding path of how it got imported does not get reflected in the data structure. So even though in main we imported from B, the owner field points at the binding in A. So it always, whenever you say import, it finds what is the ultimate binding that gets imported and points to that. Some corner cases, you can have globals that are declared but not assigned. They're basically the same as regular globals, except the value field is set to undef. Not that important, but I wanted to mention it for completeness. Okay, so if that was the only thing that we would have, this design would be fine. It wouldn't be that bad. The real trouble comes with using. So when you first do using of a module, in this case, I have a module X, sorry, a module A, again, has a constant X in it. that we're exporting. So when you first do this, there's no representation of x in the module main because we haven't actually used it yet, and in fact, you could declare it to be something else later. So before binding resolution, all we have is the binding for x in A. It has the value 1, any, and the only difference to the regular binding case is now that the export flag is set. But now what happens if you actually look at x? Well, what will happen is it'll look at main, ask, do I have a binding for this? The answer is no, and then it'll go through all of the modules that I've called using on, ask, okay, module A, do you have an exported binding called X? If so, at that point, it establishes a new binding in main that pretty much looks the same as the import binding, except it gets created lazily. So it gets created the first time anybody looks at it, rather than on the using statement as it would have been for the import statement. And this is a lot of trouble, because I said when anybody looks at it for the first time, but like, what does that mean, like semantically? And this gives you an insight into what the conversations are at the office, right? Like somebody will say something, this is a bug, and then it's like, but what does it mean semantically? So this is the question, what does it mean semantically? And the answer is, we don't know. So it was ill-defined semantically. So yeah, I will give some examples. Yes, ill-defined semantically. So before I give the example, what do I mean ill-defined semantically, right? Like obviously it happens at some point, right? Like at some point somebody's calling into the runtime and asks for the value of this binding, and then that binding needs to get resolved. And like obviously it happens. What I mean by ill-defined semantically is that in the abstract definition of the language, there's no, like we don't model as something that happens in the language binding resolution. It just sometimes happens at some point. And then this can cause trouble. So for example, something that resolves bindings is compiling a function that looks at the binding maybe. So this is an example that I like, where there's two loops that never run, but where the binding is referenced in the dead code in the middle of the loop. And the difference between these two examples is that in one example, the compiler knows that the loop never runs and never actually bothers looking at the loop body. And in the other case, the compiler doesn't know that the loop doesn't run, at least at the stage where it does binding resolution. And so it does look at X, and this causes a difference in the semantics, at least on Julia 1.11, because in the case where the compiler looked at it, you're not allowed to reassign it. In the case where the compiler didn't look at it, you are allowed to reassign it. And there's lots of examples like this. So basically, anytime the compiler compiles, and semantically, the compiler is allowed to compile at any point, is allowed to compile anything at any point. So semantically, basically, at any point in the program, binding resolution could happen. And since binding resolution has a semantic effect on the semantics of the language, just looking at the program, looking at the set of definitions without knowing what the implementation did under the hood, you cannot know what the program means. And this is what I mean by it's semantically ill-defined. Like you cannot know what the program means without knowing what the implementation does under the hood and whether it peaked at some binding. There's other things, like in the past, tab completion accidentally resolved bindings. We fixed that by hacking it so that tab completion would bail out if it saw unresolved bindings. But lots of things accidentally resolve bindings when they don't mean to, and thus change the semantics of programs. Now, is it really that terrible? Maybe not. I mean, we got away with it for 15 years, so maybe people don't encounter this in practice. But people do, like, people file issues about this. There have been 4 or 5 issues filed about this, and it's very unsatisfying. Like, it bothers me to my core. So this is also being fixed. One additional point I want to make. This can change based on Julia versions, right? Like, Yes, Stefan.
So Lilith pointed out that runs.
Which runs?
False iterates one value. Change it to an empty array.
Okay.
So everyone,
yeah. Yes. Okay, so for everybody, the correction was that there's a bug on the code. False iterates one value. Empty array replicates this behavior, though. So yes, with the slight correction, the compiler can resolve this, and it depends on what the compiler did. And also, it can change based on Julia versions. So you saw there were lots of array improvements in Julia 1.12. Those were at the codegen level, but if they had been at the inference level, the compiler might have figured out that empty array is empty, and might have stopped resolving those bindings. So whether a binding was resolved could change between Julia versions. So your package could break just because you upgraded a Julia version, and that's obviously never great. Okay. So how is this different in Julia 1.12? So we still have global ref, but I'm not showing it on the slide. But there's basically two other changes to the internal representation of bindings on 1.12. One is just semantic cleanup, making some of these cases a little bit nicer representationally. The other is that bindings are now world age aware. And the way that reflects itself in the definitions of the structs is that the using table now has a min world and a max world for every entry. The min world obviously gets populated when you write the using statement. The max world is currently, I think, always set to type max, although you could imagine that if you delete a using statement and you have revise active, it would delete it, although I don't think that currently is exposed, but that's just something that we'll add to revise at some point. So binding looks quite a bit different. So the type field is gone. The flags field is still there, but the flags all have different meanings now. But it gained two new fields, partitions, which points to a new kind of struct called a binding partition, which is basically a world age partitioned version of what used to be in binding, the type field, and what used to be represented in flags. And then there's back edges, which facilitates invalidation, although I'm not going to talk about invalidation in this talk, just because it's a big topic, and also interacts with a regular invalidation mechanism, so it requires some additional background. But those are the two new fields that are in bindings. So let's run through all of our examples again with the new Julia 1.12 design. So the simple constant has one binding partition. The kind of the binding partition is const. The restriction, so if you go back, there's a restriction field which is any typed. So in this new schematic, the bolded thing at the top is the kind field of the partition. The thing below it is the restriction. So constants are represented as a single binding, as a binding object with a partition of type const, and with the restriction set to the value of the constant. Now globals look different from that, where the value is still in the binding, but the partition says this is a global of type any. So as you'll recall, in Julia 1.11, the value field in the binding was used for both constants and globals. In Julia 1.12, that is no longer the case. The value field in bindings is used only for the values of globals, the mutable value of globals, but constants are in this restriction field in the binding partition. The reason for that is that constants are partitioned across world ages, but globals only have one value across all world ages. They might not be globals in some of those world ages, but if they are, they all have the same value. Now currently it's disallowed to actually do this syntactically, so you have to actually explicitly delete the binding if you want to switch something back and forth between being a global, and there's still some bugs there, so it's disallowed. But that's basically the plan for how this will work in the future, is that there may be many world ages in which it is global and some world ages in which it isn't, but there's always one value per binding that a global variable, if it is so declared, refers to. Okay, so now the key new feature is that these bindings are world age partitions, so you can redefine them. So if you have something that used to be const 1 and then you declare it const 2, that now simply gets represented as two chain binding partitions with appropriate world ages set, so that the min world of the second binding partition is the world in which you ran const x equals 2. So this is the simple representation of that. Import still basically looks the same, except that it got renamed to explicit, and that the import path is now explicitly represented in the data structure for import. So it no longer jumps all the way to the binding in A. It now goes through each of the bindings in turn. And the reason for that is that it needs to be able to invalidate the binding in main if the imported binding in B changed, right? Like there's lots of cases now where you could say, okay, actually the binding in B is no longer an import of A, it's now a constant, and you expect the binding in the binding in main to update accordingly, so we now need to keep track of the provenance of imported bindings. So that changed. Implicitly resolved globals, however, still kind of look like they did in implicitly resolved globals still kind of look the way that they did in Julia 1.11. And there's now a difference between the representation of things that get implicitly resolved to globals and things that get implicitly resolved to constants. So there's a whole mechanism of dealing with changes in explicit resolution, changes in implicit resolution, which is why we don't need to track this path. But basically, there's a kind implicit global, and it still points to the ultimately represented global. If it's a constant, then it instead is of type implicit const and has the value of that constant in its binding partition. The reason for that is that we allow things like this, where you implicitly use the same name from two different modules. And as long as they have the same value, we allow this. Now, in Julia 1.11, this just arbitrarily picked one of them. Whichever one happened to be first in this dictionary, that was the one that it got resolved to. And since bindings could never be changed, it didn't matter. But now we can't do that anymore because one of these might get changed later, and then we need to re-resolve the binding in main to be able to give you the appropriate error. And then putting it all together, this is sort of the complicated example, but I think if you understand this example, then you understand how all of these mechanisms work. So what we're doing here is that we're defining a module A. First, we're declaring one of these globals that doesn't have a value in it. We're using that module in main. Then we're changing the binding in A to be a constant. And then we're asking, okay, what is the value of that binding in main? So if we go through this from bottom to top, they both start out as guard. Guard is basically just a binding kind that says, okay, I looked up what this binding is, and there's no implicit import for it, so it's always undef. So basically, the very original case where there was no binding for it, that now gets represented as a binding partition guard. If it's not there, it would redo the implicit resolution and find out that it's guard. Then when we say global X, the binding in A changes to declared, but the binding in main doesn't change yet because it hasn't been using yet. Then when we do using this world age partitioned using table, the binding in A changes to implicit global. And then when we do const x equals 1, both of the bindings change atomically. The one in A changes to const, the one in main changes to implicit const, and you get what you would expect that x in that x in main is 1. So a little bit complicated on the slide, but I think if you understand all of the separate concepts, I think this should be relatively easy to understand. Okay, so again, with the correction that false on the left-hand side should be the empty array, these now behave identically on Julia 1.12. And in fact, the concept of binding resolution as something that affects semantics is gone entirely. So whenever somebody asks, whenever any part of the system asks for a binding, it now gives it a world H, and it asks, okay, what is the value of the binding in this world H? And the answer to that does not have any hysteresis. It does not depend on what ran before. It depends entirely on the set of definitions that are visible in that world H. So this is now completely well-defined. So you give me a Julia program, show me what all the definitions are, and I can tell you exactly which binding it will refer to. Whether or not somebody ran tab completion or the compiler or anything else, all of that is now well-defined. Now that does mean that it is possible that the binding resolution changed in your packages, because we had to pick for all of the various cases one rule or the other for which binding to resolve it to in cases that used to be disambiguated by a binding being resolved. Now, we've tried to pick good cases, so in most of the cases you shouldn't see this, but it is possible. However, it was also possible for this to break just because of a regular Julia version upgrade previously, because the compiler might have started or stopped resolving something. So now that it is well-defined, at least if your code works in Julia 1.12, at least with respect to binding resolution, that behavior will keep being the same in Julia 1.13, 14, and so on. So Julia version upgrades can no longer silently change the binding resolution of your bindings underneath you. So hopefully worth a little bit of pain to adjust your packages to this change. Okay, I'm running out of time, but there's, okay, so there's the whole list of things. I think we talked about each of these. Const import is a little bit weird. Undef const is a little bit weird. Backdated const is there only for compatibility and might be removed in 1.13. If you're interested about this, you can look in the source code, which has documentation on this. But I think we walked through the rest of these. So this is just here for completeness. The one last thing I want to talk about is another one of these semantic cleanups, which is latest world. So I think everybody is familiar with defining methods at top level, allowing you to immediately call that method after you defined it. But if you quote out eval something in local scope and then try to call it, that doesn't work, and you get a world H error. Now, when does this world H increment happen at top level? This is another one of these things that wasn't well defined. And in fact, the interpreter and codegen and inference disagreed on when this happened. It didn't really matter in practice because they all kind of agreed that if you defined a method, at some point afterwards, a world H increment happened. So if the only thing that respects world ages is methods, you can kind of get away with being imprecise about this. Now that structs and imports and usings and all of that also looks at world age, we needed to be precise about it. So I actually wrote documentation about this. You can look it up. There's a full list of things that raise the world age, and there's also an explicit macro core.addLatestWorld that will add a world age increment at top level if you need one, which is very rare, but sometimes if you're dealing with eval or something like this, you may need an explicit world age raise. And again, another one of those things that may have changed, but at least now it's well defined, and there's a mechanism that lets you control it. So hopefully all of this makes your life easier, and hopefully you enjoy using revise with structs. And I have 1 minute for questions. Lilith. Go ahead. Oh yeah, can we get the microphone to Lilith. And if the next speaker wants to set up while I'm doing Q&A, I think that'll save us some time.
How does this impact compile time?
Hopefully not that much. I've done a lot of work. Optimizing this. The actual impact on compile times themselves is minimal, but it does obviously add lots of new sources of invalidations. So I've added a lot of optimizations to minimize that, and try to not invalidate things if it wouldn't actually affect the resolution of what the binding refers to. But obviously there could be some impact. So it should be well worth the trade-off, but it is possible for it to add new invalidations.
Thanks.
All right. Any other questions?
I think he does have one question.
Yes.
So now that we're tracing the back edges,
yes.
How comprehensive is that, and would that open the door to automatic reference counting?
I mean, it traces the binding graph, right? Automatic reference counting would actually care about all objects.
Okay.
So there's no back edges on objects. It also doesn't trace through evaluation. So if you do, const A equals B, and then change B, A does not get updated. The thing that updates that is revise. So revise adds extra edges for evaluation, but the core mechanism in base only cares about bindings.
Okay, thank you.
All right. Thank you, everyone. Yep.
Good. All right.